Our first speaker today is going to be Arnold Rios. He's going to talk to us about number covariant many-body theory and talking about Green's function framework for symmetry broken systems. So thank you, Arnold, for starting today.
Right. Can you guys hear me and see my cursor moving around the screen?
Yeah.
All right, cool. Then, so yeah, thank you for the invitation. It was very looking much forward to being in Trento today. It's a pity we can't be there, but let's try to at least make the most of it and talk about interesting stuff at the interface between nuclear theory and condensed matter. So the work that I want to talk about today is this new non-covariant many-body theory that we're putting forward. This is the work of Mehdi Idrissi, who was a postdoc at the University of Surrey and has been for the last almost 3 years and will be moving to the fall in triumph. And really, this is sort of the opus magna, the final and the ending of his postdoc. It's going to be summarized in 2 papers that we were aiming to submit for today, but we've been a bit late, so I think I'll just wait for maybe a couple more days. They will be in the archive. It's about 60 pages of formalism, so I cannot do any justice, and I'm not going to try to summarize them anyway in any meaningful way. But I think I'll try to at least motivate why we thought it was a good idea to go through this big ordeal or through this big theoretical effort to create a new theory that allows us to formulate Green's functions approximations or self-consistent approximations to the many-body problem, not for normal systems, but for symmetry-broken superfluid systems, right? So the outlook of the talk is as follows. I'll start with a bit of a motivation on why do we want to do this in the context of the superfluidity in neutron stars. I'll briefly show some of the previous results that have been done recently, and then move into this perturbation theory and Green functions approach. So we've already heard about neutron stars in Mark's talk yesterday. So these are very exotic systems, small for stellar objects, 10 kilometers, 2 solar masses. So extremely dense and with a wide variety of different phases across them when going from the atmosphere all the way to the interior. The crust was mentioned yesterday by Alex as potentially, one of an interesting place where sort of different many-body effects could occur, and of course many-body effects that can also perhaps be mimicked in condensed matter as well. I will mostly be considering superfluidity in the outer core, where we can consider more or less a homogeneous liquid of neutrons with some protons and electrons. And what we're trying to do there is here really is quantify, the superfluidity in this liquid and possibly the superconductivity of protons. Now, of course, when you want to make this connection between theoretical physics, be it nuclear physics or condensed matter, and astrophysics, then you have to somehow connect the microscopic world with the astrophysical observations. And in neutron stars, a typical example of how this is done is provided by neutron star, structure or the mass radius relationship. So, as a nuclear theorist, I can come up, for instance, with an equation of state, the pressure as a function of the mass density, based on some model, and then by using a general relativistic machinery or simply hydrostatic equilibrium machinery if you want, by solving the Stallman-Oppenheimer-Volkov equations, I can integrate from the central point to the star all the way down to the surface, and this surface is then characterized by a total included mass and a total radius of this star. So it's a point in this mass radius diagram. I can do this again for another central pressure and then go all the way up to a higher mass and radius point, and I can go then to the highest possible maximum mass. This thing typically dips down and there is a maximum mass in a neutron star. So the left-hand side here, as I said, this is a nuclear theory quantity. The right-hand side is an astrophysics quantity and an observable one, right? So how important is then the nuclear theory's job in this case? So here's an example of how relevant nuclear interactions are. If you take as equation of state a free neutron gas, be it relativistic or non-relativistic, it doesn't change much the picture. The maximum mass that you get for a pulsar is of the order of 1 solar mass, and a radius. This would have a radius of around 8 kilometers. This conflicts, frontally with all we know about pulsars, which typically have masses of the order 1.4, and with the heaviest neutron stars that have been measured so far, which are of the order of 2 solar masses, 2.1. right? So then to go from the free neutron gas then to something that resembles nature, then you invoke nuclear or nuclear theory models, nuclear interactions, different many-body approaches, and then you can come up with different mass radius relationships. Some of them go above the 2 solar mass constraint clearly, some of them are just at the very limit. And if you have new observations like the ones provided by NICER just a few months ago, NICER is an X-ray telescope in the International Space Station, then you have constraints not only of the mass of this very heavy pulsar, but also of the radius, and this can even help us separate a bit more between these different neutron equations of state at the very least. Now, ideally, of course, you don't just want to discriminate equations of state. You want to be able to say something about the strong interaction, or even about the many-body methods that you have used to do this, right? So typically, what I've shown you are several lines, and this is what typically would have been the nuclear predictions in the late 20th century, maybe in the beginning of the 2000s. So you could have, for instance, a many-body practitioner, Alex, that liked one Hamiltonian and one many-body method, would then solve this many-body method using computational many-body theory and some simulations, get an astronuclear property like the equation of state, and put this in a black box, in an astrophysics black box, and get the mass radius relationship. Then another many-body partitioner could come along, Alessandro, for instance, with another Hamiltonian, another different many-body method, compute again astronuclear property, different line for your neutron star observation. And finally, Carlos suddenly decides to go into nuclear theory and computes, with a different Hamiltonian, different many-body theory, again, a different neutron star observation. And of course, the question is, well, okay, now you've got these 3 different lines. How can you compare this meaningfully to a point in here? The answer is, of course, you can't, because you haven't really estimated the different systematics. I mean, this is a poor man's way of estimating the systematics in their calculations, right? In the 21st century, we can do much better, at least conceptually speaking. At the Hamiltonian level, we have theories that like chiral effective field theory that are trying to give us a consistent description of the nucleon force, and in principle, an improvable one order by order. So you have a systematic uncertainty that you can understand. Your many-body theory, similarly, you could do something to try to estimate the error. An example could be, for instance, many-body perturbation theory. You do this at different orders. Perhaps, this gives you a systematic error. You go into your astronuclear property now, not just a line, but actually a band that includes both types of uncertainties. And eventually, you can even translate these into a neutron star observation. And if the observation itself has also, a probability distribution rather than just a point, and you can even meaningfully try to assess whether, the two overlap or not. And not only that, but nowadays you can even do, using Bayesian techniques, do backwards modeling. No, you can do a one step backward would be and that's what's typically done now with the equation of state, is to go backwards and get the equation of state out of the observed mass radius from, say, a gravitational wave observation. And ideally, if this is well under control, then you could even do another step backwards and try to go back all the way down to the many-body method or the Hamiltonian. And the point that I want to make in this talk is, at least for the things that are not so much affected by superfluid properties, like the equation of state, which you can essentially compute in the normal phase, this sort of procedures of going forwards and backwards is more or less well established now in a more or less systematic way. You can discuss, of course, how you create these uncertainties, but at least people are providing those. And my point is that, in the superfluid phase, this is happening less. And part of the problem there, or a significant issue there, is the fact that the many-body method uncertainty is much more difficult to quantify, because there's not such thing as a well-defined many-body perturbation theory or there is, but it's complicated to implement at least. So what we want to do here is to try and simplify this in some way or another. Right, so let me discuss then, what we typically do in the normal phase. For instance, in a self-consistent Green function scenario, you fix your density, you fix your temperature, which has to be about the superfluid phase transition. You can incorporate 2 and 3 nucleon forces, because in nuclear physics, we need those 3 nucleon interactions for a variety of reasons. You can then put this in an in-medium interaction, a T-matrix, for instance, in the medium that would look something like this. And what we know is that this T-matrix shows a a pole or there's a singularity that appears if you were to go very low in temperature and below the superfluid temperature, signaling the fact that this self-consistent Green functions approach has been devised in the normal phase, not in the superfluid one. And there is a long history of application of these types of methods in nuclear physics, and all of them have had to sort of live with the existence of these superfluid Cooper pairs in different ways. In this specific case I'm mentioning, we're doing this at finite temperature, so we avoid completely the Cooper pairs. The medium interaction can then be used to compute a self-energy. You use the Dyson equation to compute a propagator, and then you iterate this at the given density and temperature until you get consistency. And out of this, you can get several interesting properties. You can get spectral functions, momentum distributions, thermodynamics, even some sort of transport properties. And that we can do for symmetric matter. This is matter this is the equation of state of symmetric matter, same amount of neutrons and protons. And on the right-hand side, which is more relevant for the neutron star, this is neutron matter, only neutrons as a function of density and the pressure in here. And you can see different lines here correspond to different interactions that come from this chiral effective field theory. So in a sense, this represents some sort of error band associated at least to the Hamiltonian. You could do this with different, you could do this at second order, you could do this in the T matrix level, and you could then also come up with many body uncertainties for the equation of state. This has been done. And you can do that at finite temperature. And then if you have several finite temperature calculations, you can even be bold and try to extrapolate to the zero temperature regime, which we have also done, because then you get the spectral functions, self-energies, and momentum distributions, which perhaps are not really valid around the Fermi surface where you expect superfluid effects to play a role, but away from it can inform you about things like the depletion of the Fermi surface and short range correlations and occupations of high momentum states. And sometimes then you can use this further on to characterize superfluidity. Right, so this is sort of the spiel for the equation of state and for the state of the art in self-consistent Green functions, more or less so far when it comes to applications in infinite matter. Now, cooling or superfluidity matters for neutron stars in a variety of aspects, and cooling is probably the most important one. So this is a typical diagram of the cooling curve of neutron stars. What you have here is several points. All of these points represent different pulsars for which we have historical records that tell us, when the associated supernova to that pulsar exploded. So for instance, Chinese astronomers saw the crab explode about 1,000 years ago. That's this point. You can then measure and put an X-ray telescope, measure the surface temperature of the crab, and then that comes this point. And then you can do this for different sources, different pulsars, and you can see that it seems that with age pulsars seem to cool down as you would expect them to do. And then you can sort of try to model this cooling in different ways. This is what this red line does. And the important thing about this cooling curve is that it is supposedly sensitive to the interior physics, right? So for instance, here's an example of a curve. Here are the ingredients that curves, for instance, that are relevant for the cooling of a specific neutron star. This is Cassiopeia A. This would be, ingredients like the mass, the equation of state, the internal composition, the pairing gaps, and the atmospheres. And in this specific plot that I'm showing here on the top right, what the astrophysicists did was to completely forget about the consistency between the equation of state and the internal composition and just simply change the pairing gaps. And you can see that by changing different pairing gaps, you get very different cooling curves, and some match this sort supposedly rapid cooling of Cas A at the present time, right? Basically, these are observations, very recent observations of Cas A with X-ray telescopes. There was even a paper today on the archive discussing this rapid cooling. So just to tell you that this is a hot topic. Now, this rapid cooling occurs you can associate this to pairing because there's effects like this Cooper pairing that show up when you can imagine you're lowering the temperature of the star, and then at some point you hit the superfluid phase transition, you start forming Cooper pairs. This and then this energy from the Cooper pair is released into the medium in terms of neutrinos, and that helps cool quickly. So different pairing gaps can give you different cooling curves, as you can see. On the left-hand side here, what you see is the plethora of predictions coming of lines. Now, again, there's no systematic uncertainty here. These different lines, these are different names from the different practitioners that decided to put together different interactions and different many-body methods to compute the pairing gaps in the triplet channel. You can see there's a variety. These things change from a factor of 2 in the range, or in the peak, but also in the whole range of where the pairing is active. So that's difficult to estimate. Uncentered is associated to the interaction can be more or less assessed nowadays. So this is an example from the Darmstadt group, for instance, where you can see on the left-hand side singlet gap as a function of Fermi momentum, and the right-hand side triplet gap as a function of the Fermi momentum. You can see on the singlet graph, all of the curves more or less give similar behaviors, whether you input or not 3 nucleon forces. The peak is more or less the same. The closure is more or less the same. The right-hand side, on the other hand, gives you large uncertainties, which is already telling you, well, P and F waves perhaps are not very well constrained with chiral effective field theory. That's an important message. But all of this has been done in a kind of a BCS-like picture, right? And one, of course, can question whether the BCS theory can be used directly in the interior of a strongly correlated system like Newton stars. So typically you solve an equation like this, which is a gap equation with the matrix elements of your pair interaction, and then a denominator, which in this case has been computed with a kinetic energy and a Hartree-Fock spectrum, right? Again, this doesn't really allow you to say anything about the many-body uncertainty. Can you go beyond BCS, for instance, and try to assess how big these different uncertainties would be? We've tried to do that. I tried to do it at least with some sort of Green's functions theories, in which you at least get the spectral function from the normal phase and somehow plug it into a BCS type of equation. And what you see then is that the fragmentation of the single particle strength along the Fermi surface reduces the pairing. This is what you see here, going from the left-hand side where you have BCS to this short-range correlated theory on the right-hand side. So you've depleted the maximum and also a little bit the closure of the gap. This happens both in the singlet and in the triplet. But again, this is just some sort of extrapolation from the normal state into the superfluid state. There is nothing really, telling anything about the superfluid state into the normal state or any sort of self-consistency there. And in the end, we are left with more or less the same picture of a plethora of predictions for gaps beyond BCS, right? And it's difficult to say anything meaningful here for astrophysics. So in this context, what you would like ideally is to create a theory that allows you to treat symmetry breaking, that allows you to do this at finite temperature, that has a systematic expansion, including 3 nucleon forces. And that's exactly what Mehdi did. And it's been a painful work, as I said. It took over 2 years to get there, but we've managed to more or less at least come up with the formal steps. Let me try to briefly summarize this in the next few minutes. So ideally, we start basically with a very similar state to what you would do with, say, Nambu theory, in the Nambu typical theory of superfluidity. You have 2 sets of single particle bases. They are orthonormal in everything that I will preserve in here. They don't really necessarily have to be. These 2 bases are related by a given involution. So 1 takes to 2 and 2 takes to 1. This is similar to what you would have, say, conceptually, I guess, in the Gorkov case, where you have a single particle basis and then the time reversed basis. That would be this star notation. This is kind of same idea. Then you define global indices, mu and mu prime, and then you get your Nambu fields. And then you define Nambu fields, which can either be contravariant or covariant. And here's where you start to see slightly different notations with up covariant and contravariant notation, with canonical anti-commutation rules that are performed by both the canonic, the covariant, the contravariant, the covariant, and the mixed phases. And the reason that you want to introduce these covariants is that then this allows you to create a theory where Bogoliubov transformations are implicitly respected or taken into account, in a sense. So you define now your objects as tensors, as you would do normally, except that now these tensors are the tensors are defined by the transformations themselves, and the transformation in this case is just the general Bogoliubov transformation, which in itself also includes potential changes of single particle basis. So in the end, what you're doing here in creating this tensor structure is having something that is independent of the Bogoliubov transformation on the basis. You can then define tensors as you would do normally by looking at how indices change. You can have a P contravariant and Q covariant index tensor, for instance, that would change in a Bogoliubov transformation in this fashion. You can then define operators as you will see later on, it's convenient to look at things that are fully covariant, for instance, in the matrix element, and fully contravariant in terms of number indices. And then you have an associated metric tensor, which in this case is basically a delta Kronecker on this involution of indices over there. And this metric tensor plays the usual role. You can see that it also helps you raise and lower indices as you would normally. This is all quite complicated, of course. So typically you don't express superfluidity, perhaps in terms of tensor algebras. Why would you want to do that? As I said already, you can get Bogoliubov expressions that are independent of the Bogoliubov transformation, but also because then things become very transparent and in terms of new tensor networks, right? In modern languages, all the expressions that we will obtain towards, are essentially just reductions of tensor networks obtained by tensor products or tensor contractions. And as I will just show you in a minute, this also leads to a nice diagrammatic structure. To get these diagrams, what we do is to perform a partitioning of the Hamiltonian. We only require a quadratic reference Hamiltonian. I talk about Hamiltonians, but of course this could be grand potentials. These are symmetry broken states. This needs to be quadratic in number fields. Yes.
No, just quickly, just to remind you, I have 5 minutes to.
5 minutes. Yeah, thank you. I'll try to wrap up as quick as I can. We have one interaction terms that involve covariant k-body vertices. So this would be like a k-body force here. K equals 3 is a 2-body force. K equals 3 is like a 3-body force. We can define fully contravariant Green's functions then as the usual time-ordered set of 2k number operators, and these are average with respect to your thermal expectation value. You have a perturbed and an unperturbed Green's functions, and you can connect the two of them using the interaction picture and your standard perturbation theorem. Again, you use statistical Dick theorem and the linked cluster theorem like you would do in the normal phase, and expand all of this in terms of Feynman diagrams. A subtlety here is that it turns out to be very beneficial to work in a setting where you don't have oriented fermionic lines. And the price to pay in this case is to work with fully antisymmetrized vertices. So these are fully covariant vertices where you antisymmetrize with respect to all the lines, not only the incoming and the outgoing lines as you would do in a Hugenholz diagram, but also in the incoming and outgoing lines. Let me just hopefully show this by diagrams. If you have unsymmetrized vertices, the Hugenholz antisymmetrization would take care of this type of exchanges of the set of the final state lines inside of any Fermi diagram, of any Feynman diagram. What we are interested in, though, is to be able to perform this full antisymmetrization, not only with respect to incoming and outgoing, but also across the interaction. This, of course, you can do. You can always define. It's a one-off pre-computing cost. You give your matrix elements, you pre-compute this antisymmetrized vertex, and then you can, at the price of doing that, then you can develop a theory that has no knowledge of the directions of your fermionic lines, and that turns out to be very useful. We can perform Feynman rules. We come up with the right symmetry factors. We can even perform the Matsubara sums using Godin rules. And just to give you an idea of the simplifications, if you start with an HFB reference state, a Hartree-Fock-Bogoliubov reference state, up to third order in your Green's functions, you only have really these three diagrams, one at second order and two at third order. So everything becomes much more simpler. To give you an idea, if you fix two of your external number indices in Gorkov Green's functions, you would have something like those 6 diagrams instead of one of the diagrams that I'm showing here. And with the additional advantage that, of course, all the expressions that we get are really invariant with respect to the change of Bogoliubov transformation. So this is a formal simplification. I'm not going to go into the details of how to do perturbation theory. Just trust me. Basically, you can go. We've shown up to third order diagrams in the paper. Then you can ask yourself, can you also do something like you would do in the normal phase of a self-consistent Green's function cycle? And the answer is yes. And it basically boils down to the same structure that you would do in the normal case. You introduce a self-energy, which is the connected part of your Green's functions. You get an expansion now in terms of 2 particularly reducible diagrams of dressed propagators. That's all kind of standard. I'm just going to skip this part, which is interesting, but that doesn't add too much. You can also look at your 2pi action if you want, and in the lowest order approximation in which you approximate this to be your interaction, you can define very similarly to as you would do to the normal phase fully covariant T matrix if you want in this case, or a T matrix formalism that you can again invert. So here in what we are proposing then as a sort of alternative in the superfluid case is it works exactly the same that you would expect in the normal case. You have a bubble propagator that defines T matrix. This T matrix defines, you can get a self-energy out of this T matrix. You can then get a propagator from this self-energy and insert this back, iterate until a given point. And if everything goes well, then you should have access to not only just the normal components of your propagator, but also all the anomalous ones as well by taking different orderings of those global indices and number indices. And the expressions that come out when you take into account these full covariant properties are basically very similar to the ones that you would get into the normal case. So, you know, formally equivalent. All the complexity of the symmetry breaking is encoded in these indices here, which need to be treated. But again, all of this is sort of a pre-computing cost that you can take care of. The self-consistent cycle is not more difficult than it would be in the normal case. So just to conclude, I talked very briefly about what we can do with self-consistent green functions in the normal phase for neutron stars. We can compute equations of straits, spectral strengths. We can even say something about the pairing properties, but really now what we are pushing forward is a new formalism that can take into account symmetry breaking with a simplified perturbative expansion, and that allows also for self-consistent resummation. So now we can not only do, say, second order, self-consistent second order, we could do also self-consistent T matrix, and with that at least try to give some sort of, try to pin down at least the uncertainty in the superfluid phase coming from the many-body theory, in addition to what you can already do with the Hamiltonian. All right, so thank you very much. That's all.
Okay, great. Thank you very much for the nice talk. So we will open for a few questions from the audience. So anyone? Okay, Piotr.
Hi, Arnold. I'm wondering whether you compared your results with some standard HFB, and how does it work?
Sure. At the HFB level, there is no real. At the HFB level, with two-body forces, you essentially get the same equations that you would get, you know, in a standard nuclear physics simulation. One advantage of the formalism is you can explicitly include three-body forces. It comes out almost automatically, and you can do that as well. We haven't got there yet in terms of the simulations. We are working on that, and now we have to sort of, first of all, do all of this in the partial wave basis, and then do the numerical implementations. But it turns out that the equations at the HFB level are exactly the same, right? I think that the advantage here is when you try to go beyond HFB.
Mm-hmm. Thank you.
Maybe I can ask a question.
Yeah.
So you said the numerical implementation is still to come. Do you foresee any messiness in comparison to the self-consistent Green's function implementations already in place?
Right. I think we are trying to be hopeful and optimistic and thinking that there won't be, I don't think there has to be, I mean, the self-consistent Green functions as it is in the normal phase, it's quite messy, and there's a lot of complications in there. I don't think there is anything extra. As you can see, formally, the equations that have come out are exactly the same. But the devil is always in the details, and we'll have to see exactly, you know, when we get there. So far, what Mehdi has done at the form, at least in the implementation in the partial wave basis, for instance, which is what he's working on now, seems hopeful and positive. More or less everything stays at the same level of complexity.
Excellent, thank you.
Okay, so any more questions? I have someone, a couple of questions quickly, but let's get the audience. Anybody else would like to ask? Okay, so I'll ask a quick one. I think Alex asked something. So we're still in the implementation phases to really compare things with other methods. So it's hard to say anything right now, but there's a very nice structure. I think that's interesting.
Exactly.
So I think I understood that. So I had one question. I saw something in your plots at the beginning, the plot of pressure for the proton-neutron system.
Sure.
And I noticed that you have some, if I'm wrong, I mean I'm wrong, you have negative pressure on those things.
Oh yeah, sure. In the symmetric matter case, you can have negative pressure. That's correct.
Right.
Yeah.
So can you what physically happens in that region?
There is a phase transition. There is a liquid gas phase transition occurring in that region. Nuclear matter is not supposed to be homogeneous at that stage. They're stable, exactly, and it condenses into nuclei essentially, right? So
okay. So that was just indicating that you have that thing. So
yeah. So I'm trying to get there. Sorry, the slides are slow. Yeah, exactly. This is just indicating that
you had neutron matter by itself. The pressure was well defined, but
the pressure is always
of neutron proton.
Right. Exactly.
Definition of a negative pressure, but that depended quite a lot just on the specific model that you're using. Some of them seem to give you right.
Correct. The critical temperature for this phase transition depends strongly on the nucleon force that you are using. For instance.
You're using right.
Yeah.
Okay. And so not only the amplitude, but presumably also on the range. In those curves, it's just changing how strong the forces are. Is that right?
Right. So the critical density, the critical temperature, they all depend on the many-body formalism that you use, because of course, and the interaction that you use as well. So there is error uncertainties coming from both aspects in there, and we've looked at those. We've in my PhD student Arianna Carbone looked at all these aspects of the liquid.
That's good. I'm just curious because I saw the negative pressure there. Yeah. Okay, so thank you very much, Arnold, for the nice, interesting talk. I think we should move on to the next talk. Francesca, I hope she's there. Hi, Francesca, how are you?
Hi, very well.
Okay, Francesca is going to be our next speaker. We're going to have the plan is about 20 minutes, Francesca. Then I'll give you 5 minutes to wrap up and 5 minutes for questions from the audience. So Francesca is going to give us a talk about two-dimensional supersolidity in dipolar quantum gas. So thank you again. So we can go and start.
Okay, thank you very much for the invitation. So I've decided to have sort of a more extensive introduction to the problem and a rather short wrap-up time. I hope this is okay. We are kind of really changing a little bit gear here, because the idea is to speak about quantum gases, so gases of many particles that can both condense and having a many-body interaction between the particles. And so the underlying idea, one second. The underlying idea is which type of quantum phases matter can be realized using quantum gases where the particle interact via long range and an isotropic interaction, the so-called dipole-dipole interaction. And I would like to give you an example of one state that we have now studied in the last couple of years in my lab, which connect to sort of a question, a theoretical question that it's more than 50 years older. And in this theoretical question, I would summarize as Leggett have done with the question whether a solid can be superfluid. So there have been, let's say, a longer theoretical debate whether two different symmetry can survive and live together in some quantum state with a many-body interaction. And so to try to give you, let's say, an intuitive, how should I say, definition of this state. This state is called the supersolid state of matter, and is a state in which the system is expected to break simultaneously two different symmetry. On the one hand, it would appear the crystalline order, which is proper of a solid, and at the same time having Bose-Einstein condensation and superfluid property, which is proper of, for example, a frictionless flow. And so this was a highly debated theoretical question, and there have been early work actually excluding the existence of such type of state. So a state here, it's our, I hope you see my mouse. So is a state which kind of merged together the idea of the crystal and the idea of a superfluid. And so on the one hand, you have a breaking at that point to localization, which of course costs energy, and on the other hand, this frictionless flow. And so the early work back in '56, I mean, there have been several work, I just quote one from Penrose and Onsager, actually excluding the existing of a single many-body state in which these two orders can live together. However, soon after, theoretically, it was actually predicted that quantum mechanically, such type of state can be allowed. And so there are very beautiful work I want to highlight, in particular the one of Gross in '57, but then a series of other work following, in which actually they have been shown the possibility of having Bose-Einstein condensation and, let's say, quantum crystal at the same time. So this is, of course, a very paradoxical state of matter, which results really from the properties of quantum mechanics. And there is an important point is to then to see how this type of state can be observed in experiment, whether the parameter region where different solid state or a condensed matter system can actually realize this state. And so the first system to be considered actually was a solid, and to maybe cooling down this solid and, let's say, having a Bose-Einstein condensation of, for example, a vacancy in a solid. And so then the relevant question was really at the early time of experimental investigation in this field, whether a solid can be superfluid. And there have been especially work in a helium solid. And just to give you an example, there have been a work in published in Nature in 2004 by Kim and Chan, showing about the probable observation of supersolidity in solid helium. Because, I mean, this observation was related to an anomalous change of the moment of inertia that would be compatible with a frictionless flow in the moment of inertia. However, this result, which has a lot of impact in the condensed matter community, was also highly questioned by a number of experimental and theoretical work. And it turned out that the reduction of the moment of inertia observed was rather related to the imperfection of the system. And indeed, a very nice example of, let's say, how, let's say, scientifically challenging are this type of experiment for experimentalists is that the same author, about 8 years later, published another follow-up paper using a much more developed and advanced experimental setting to actually confirm that the early observations were not related to supersolidity. Of course, one of the points here is, let's say, in real solid, is somehow how to, let's say, distinguish the role of imperfection or the role of impurities that you can have into the system. And somehow the tunability was in some sense limited. And so theory work have been developed to try, let's say, to see whether there is another type of platform that can be more appropriate to enter this very exotic phase of matter. And so the question kind of, there have been a change of paradigm, and the question became in later study whether a superfluid can be a solid. So there is this shift of thinking to start from a superfluid state and to eventually see if it can break a translational order and, for example, develop a density wave modulation or develop a special modulation which would kind of be compatible with the crystalline order. And here I'm just listing a number of key players in answering this type of question, but the list is actually very, long. And so this is where we start. And so what do you need to have a superfluid to, let's say, break translational symmetry? I mean, I like very much this background photo because it gives a sense of what we are looking for, what we are hunting for. So we want to have a fluid with many-body interaction that is superfluid and that spontaneously, let's say, make emerging a density pattern into the system. And so the density pattern have a very regular spacing. I mean, you can say the pitch of lambda star, and it's very regular. And so this would tell you that the wave function, which is, let's say, this the background density, has symmetry different from the Hamiltonian. So this is in the sense of a spontaneous symmetry breaking. And so how to get a system having the possibility to break the translational symmetry? Well, it is now clear what are the ingredients. And so maybe the first more important ingredient is that you would like to have a state, a superfluid state, which have a many-body interaction between the constituent, which are dependent on the momentum. And so this type of very general requirement can be realized in very different platforms. So indeed, you can have Rydberg gases, or you can have Bose-Einstein condensate coupled with light. For example, if you put a Bose-Einstein condensate in a cavity, or you can have a spin orbit coupled Bose-Einstein condensate. And the system that we in the lab are interested are the system composed of atom with large magnetic moment, because the magnetic moment add another interaction among the particle, which is the dipole-dipole interaction. So looking a little bit more in the detail on this interaction, this is the standard formula for polarized dipole, in which you have a dependence on the angle. So this interaction is anisotropic. It can be either attractive or repulsive depending on the alignment of the dipole, so whether there are head to tail or side by side. And there is a very peculiar, let's say, dependence on space, and it's falling down as 1 over r to the cube. And this is in 3 dimensions. This is a long range interaction. Now, what is important to notice and to add in addition to this problem is that if you would have, let's say, a sphere, and you would put all your dipolar particle in a sphere that is confining, for example, a setting of many-body particle. So you might have that you have as much as traction as repulsion. So integrated in a let's say in a spherical symmetric environment, the dipole-dipole interaction will basically vanish. And so in some sense, if you are in a uniform case, the momentum dependence is not explicit of the dipole-dipole interaction. It's just come up from the angle dependence. But then in the integration, this would wash out. Differently it is if you don't go to the uniform case, but you, let's say, start to compress your sphere. You make maybe a 3D ellipsis in one direction or in another. In this type of geometry, you kind of are favoring one type of alignment, where here the interaction would be negative with respect to another type of alignment. And so when you have an anisotropic confinement that can be, let's say, really a pancake or an ellipsis, so you start to have an explicit dependence on the momentum. And this is exactly what we would like to have. So if you use in the experiment external trapping, you can shape the volume of integration of this interaction. This is how you get the desired momentum dependence in the interaction. A second interesting point is that in this dipole-dipole interacting gas, you don't only have the interaction coming from the large magnetic moment, but you have also the usual molecular interaction a la van der Waals, which in the ultra-cold regime turn out to be a constant. It's called contact interaction, is not extensive, it does not depend on space, and it's almost a constant, which have in the physics I will show you later as, let's say, the role of making an offset and controlling by an offset the different phase of matter that can be reached. Now, if the potential is momentum dependent, of course, if you look at the dispersion relation, so here it's energy versus momentum, the spectrum of excitation, let's say the Bogoliubov spectrum of excitation, for example, would have also an explicit momentum dependence via this interaction. And now back in 2003, it was shown by theoretical colleagues Santos, Shlapnikov, Levenstein, that the spectrum of excitation is changing substantially because of the presence of this moment-dependent interaction. And in particularly, the spectrum of excitation would, let's say, dig a minimum at higher momentum. So you see that if you now the spectrum of excitation, you can interpret like you drive energy, you put energy into the system, and you want to know which are the excitation that you can trigger into the system. And there is a specific momentum where you have a minimum, which is called the Roton minimum, where actually the energy cost to create this excitation is smaller than the one, for example, you would need at smaller momentum. And so this minimum is very reminiscent of the usual Roton spectrum a la Landau that you find in a helium superfluid. And moreover, this the contact interaction, so this additional constant offset, you can use it to, let's say, control the energy gap. So the momentum does not really change. So the minimum is set by the dipole-dipole interaction in the trap, but the size of the Roton gap, so this energy gap, you can control by changing the contact interaction. That is something in our labs, I mean, in the ultra cold labs, it's easy to do, and we know how to do this type of tuning. And so it has been a long way for the experimentalists to be able to prove the existence at all of this Roton. And here I show you, let's say, the observation of the full energy spectrum of a dipolar gas, where you see that by changing the scattering lengths, you can go from something which do not have any quadratic minimum to something that flat down and then eventually start to really make a minimum into the spectrum of excitation. But all these type of spectrum are excitation, let's say, on top of a Bose-Einstein condensate ground state, which is homogeneous, let's say, or non-modulated. And but somehow one can ask what happens if the Roton excitation softens completely, in the sense that the Roton gap is completely closed. Now, the first consequence, very easy to see from the dispersion relation, is that in particular, you need no energy. There is no energy cost to create this excitation. So there is a tendency of the system for every small thermal of quantum fluctuation to start to populate this high momentum mode. And indeed, you would see that although the ground state, let's say, is simply an inverted parabola because we are trapping in an harmonic trap, the system will, due to this quantum or thermal fluctuation, make emerging this little, let's say, density modulation on top of the unmodulated background. This is all an excitation. And so this density modulation you can see as a matter wave. Wave interferes. So if you look at the momentum distribution, since there is only one wavelength of this modulation, you would see, let's say, two additional peak in the momentum distribution corresponding to the K rot plus and minus, because the total momentum, of course, should be conserved. And so this is what we also observed in experiment, even before mapping the full spectrum. What we saw is that for some given value of the scattering length, the momentum distribution start to clearly appearing this side peak of the Roton momentum. At this point, there is another question that one should pose, and is the very simple one as well, because if it's there is no energy cost to create excitation, and there is an initial finite population, so you will have, according to Bogoliubov, an exponential increase of this excitation. The system becomes unstable. This instability is known in literature as the Roton instability, and basically this would give you a sort of Roton collapse of the system. And so it would be in some sense game over, because the ground state would not be then really well defined anymore. However, and here comes the third very important ingredient, what it turned out, following a suggestion, from a paper in 2015 by Shlaknikov and Petrov, that if you have the Rotten instability, but for some reason there is an additional repulsive interaction into the system, which grow in power of density faster than the usual, let's say, mean field, meaning contact and dipolar interaction, this term, even if it's small, so the coefficient G3 might be small, it has an important role of stabilizing the system. So instead of, let's say, growing at the height of the density modulation, it will set a cutoff on the density and stabilize the system. With the presence of this stabilization mechanism, you will have that the system undergo a phase transition to a novel ground state, which is the one interesting for us, which is the supersolid ground state, indeed. So the ground state itself will become now density modulated, and the density modulation is just due to the interaction, nothing to do with the way we are, let's say, confining the system. And so in this early paper, it was thought that this term is a genuine three-body forces. In cold atom, genuine three-body forces can be hardly, let's say, established at the moment. But what was found out by also work in Stuttgart is that there is indeed a protection mechanism, which is called, which is nothing else that the first order correction to the mean field. And this is called quantum fluctuation. This is a repulsive term. It can be, within the mean field, the description can be described in terms of the Li-Wan-Yang term. This is how it's known, and has been demonstrated in a different type of dipolar system and geometry, but still is a very general additional term. So it's the first correction that play a very big role when the other two mean field interactions start to, let's say, compensate each other. One positive, one negative, this term remain and set this cutoff physics. And so when you put all these ingredients together, what you see, and these are our simulation based on the extended GPA with Li-Wan-Yang included, that the macroscopic state start to create density wave. So in the infinitely elongated case, or in the uniform case in two direction, this type of modulation survives. So it's not an effect of the finite size of the system, but of course, having a finite size system, a real system with finite number of particles, the number of density modulation are kind of limited. And so, and indeed, already back in 2018, we kind of saw, in some sense, early hint of a supersolid state. Because as I told you, without the protection mechanism, you would imagine that the population, this is in the y-axis, like the population of the Rotten mode, the population will exponentially grow. But what we saw is that after an early time dynamic where the mode was very fast, the Rotten mode were very fast populated, the growing stopped, and it started another regime of very slower dynamics. And so, and we pointed out even in the conclusion that indeed the quantum stabilization can actually favor the formation of a supersolid phase. These early hint and the speculation have been then shown by a theory work of Rucuzzo Lancillotto exactly for our parameter of this experiment that I'm showing here, showing indeed that there was this supersolid new ground state, supersolid ground state in the system appearing. Then there was a sequence of much more dedicated experiment to try to pinpoint the region of existence and also to establish in quantitative manner the existence of the supersolid state. And here I point out of simultaneous work from my group, the group of Pisa by Giovanni Modugno, and the group of Stuttgart by Tillman Fau. And so, and here you still have phase coherence. So it's there is a macroscopic phase describing the system. And so there is a breaking of the gauge invariance, and there is a density modulation, spontaneous density modulation, which is pointing to the breaking of the translational invariance. How do we observe this?
Just quick, just 5 minutes to wrap up this slide, you know.
Yeah, okay. And okay. And okay, so, and now our observable, let's say, is now we can look really at this modulation intercept, and we can look at the time of flight image. And so maybe the point I would like to show you is that the observation of supersolidity, the study of the excitation, was all done in a system. You have to imagine a 3D system, which is an ellipse, like we call it cigar shaped. And so in this
you
case,
might want to share your screen. I'm not seeing anything. Anybody see the screen?
Sorry. Oh, yeah, right. Let's see. Yes, so in which the density modulation, actually, it's really breaking only in one dimension. So the density modulation you would expect in the weak direction here, so this elongated direction. But actually there was a big question whether, let's say, you could actually make a bigger system, bigger supersolid, and in particular, if we can really go to 2D. And this is what, I mean, have been the observation of the last couple of months in our lab. To do this, I mean, we had to, the trick was to change the type of trapping and to go more and more toward rounded trap. And so we call it from, let's say, a kind of a cigar, we go to a more surfboard trap. And now I want to show you how the ground state, because this is in each value of the trap, we directly evaporated into the supersolid state. There is no tuning of the trap or of the scattering length. And you can see that now if you move from cigar to surfboard, at the beginning nothing happens, and then you start to see that the transverse directions start to, you know, have some not splitting, but really two droplets appearing. Then if you go even more, you start to see more and more. And then also in the Fourier transform, you see this additional peak giving you the crystalline structure also appear in the other direction in a very clear manner. And actually there is a full spectrum of excitation. And the first question is, now that we see this kind of also transverse direction, so in two directions, the symmetry splitted, whether it's phase coherent. And now we saw in the phase coherent state that actually the density, the matter wave interference is fully phase coherent. And we have a lot of different measures to prove this, in contrast to the case of incoherent droplet where the density, let's say, so the pattern of the interference pattern wash out. And you have all a spectrum in which you have very different ground state going to this very extensive ground state, which is really look like very much, let's say, completely symmetric. And so this is what then we did. We changed more our trap to give even more atom and to have even more droplet. Now you see it start to become more extensive instead of this two line I showed you before, it's kind of growing. And then we also changed our trap geometry. This is a simulation to try to have this type of shape, and we move it to a fully circular trap. So we did this, was a challenging in the experiment, but we changed the trap, and this is what we expect in the experiment. Exactly, I mean, how you would expect from the theory. So you have all this, and this is all phase coherence. And so just to show you maybe a video of how the evaporation proceeds, which I think it's very nice. So here you have a thermal cloud. There is no Bose-Einstein condensation. This is stochastic GP approach. And then at some point in the density, you start to have that the system is cooling down, the density starts to increase, and you have this first droplet appearing, but still they are not phase coherence. The part below is the phase coherence. You say it's too colorful. Each color is a different phase. So there is a point in which you have a crystal, but you don't have phase coherence. And then you see now it starts to become completely homogeneous in color, all red or all blue, or all green. And so, and here you get in this fully, let's say, phase coherent state. So the phase is uniform and the modulation is clear. And so now this is what I wanted to show you. Sorry for the problem. And before the problem with the connection, I would like, thank you. I would like to show you the lab that actually did all this 2D physics experiment, which is the Ibm Dysprosium Lab in Innsbruck. And of course, many of the work have been also done in the Ibm team and in collaboration with the new established theory team in my group. And with this, I would like to thank you.
Thank you very much, Jessica, for a very nice talk. We will have a few minutes for questions. So please, from the audience.
Okay, I can ask a question. Maybe I also saw my picture. Oops. No. Hi, Francesca.
Hi, Paolo.
Hi, nice to see you. So these are really amazing, this 2D. It's like, wow. Cool. So how cold temperatures do you need to go there? And was it any problem like to achieve those temperatures, or is that not a challenge at all?
No, so actually it's really amazing. So the scattering lens is set by a magnetic field. You have your thermal cloud, you go to the magnetic field where you expect a supersolid 2D, a 2D supersolid, and you just do evaporative cooling as it would be the normal Bose-Einstein condensate. There is no theory telling us a formula, let's say an analytic formula for the critical temperature, because that's a modulated state. But I mean, we start to see this effect really in the same range of temperature that you would expect for normal Bose-Einstein condensation. Okay. So it's absolutely no challenge, no trick, and nothing really. It's a normal, the same ramp. We use the same ramp of condensation from the unmodulated BC to the isolated droplet array to the supersolid in 2D. It's exactly the same. You just need a lot of atom.
Yeah, that's amazing, because usually when you put some extra on top of a usual BC, the critical temperature would go down, but apparently it works.
No,
okay. Yeah, thanks.
Luca.
Yeah, thanks.
You ask your question.
Yeah, thanks for the talk, first of all. So I wanted to ask, so the system at the end, it seems to me from the experimental picture is quite small. So like about 4 or 5 modulations. And then so does it already break the translational symmetry? And then how do you prove that the symmetry is spontaneously broken? Like, do you do many repetitions and see that the phase is always on a random position?
So first of all, it's not 2 or 3. No, you see here, you have many more droplets. Let's say all this is, let's say, density modulation. So the yellow is high density and the black is low density, okay? And second, yes, you can do, so the phase have nothing to do with the modulation, let's say. But actually what you can do is, let me, see.
Sorry, by phase I meant the position of this lattice which comes out.
Yeah, it's all, I mean, the position is repeatable. So the K, the wavelength of the modulation is stiff, in the sense that it's not changing shot to shot. Is the roton, is the so in the 1D is the roton, in the 2D the situation is more complex. The phase transition is not a soft, let's say, first order or even continuous, is really a very real first order transition. The K is always the same. The wavelength is always the same. Then by looking at the interference pattern, you can, let's say, take the phasor, the complex phasor. So you take the interference pattern, you do the Fourier transform, and you get the phasor. Now this phasor has an amplitude and a phase, a global phase. So the amplitude, and then from this you can extract 2 quantities. This method we have developed is very reliable. One is, let's say, the modulus of the phasor. So it means the phase doesn't have any, it's the modulus of P. The phase doesn't play any role. And then you take hundreds of pictures, and this tells you about the modulation. And the other one is doing the contrast. You take 100 pictures, you make the average. So the phase is let's say, surviving, and then you take the modulus. And here there are 3 examples. If you would apply this protocol to a state which have no modulation and no phase coherence, and then you plot, let's say, in this, let's say, polar plot, the phasor, you would see that all the points, every point is 1 experimental repetition, will all collapse in the center. There is no radius, really. Let's say it's very concentrated. While if you have a state with modulation but without phase coherence, you see that there is a finite radius of this circular of this distribution, and but there is no preferred phase. Now, if you go to a state which is modulated and phase coherent, then you see that there is it's not anymore 360 degrees spread, but it's focusing in one side.
Okay,
And
so basically you can see that this in momentum space, like this.
I can see in momentum space, and since you are asking on the, I can see momentum space, and I can really see in real space, because if I now, so I can see from a thermal cloud how this modulation emerge directly from the thermal cloud. So I can see the in situ distribution, really in real space, the wave, how they develop, and then I can study in momentum space the coherence of the state. Yes.
Sorry if I take so much time. I mean, you can see the spontaneous nature of this in momentum space, but not in real space.
What do you mean not in real space?
I mean, just asking if you repeat this picture on the.
This is in real space. The one you see here is real space.
Yes, but would they fluctuate if you repeat the experiment? Or
would they fluctuate? The spacing is stay the same.
But the position of this lattice.
The position, I mean, if your dipole trap is stable enough,
okay,
it doesn't fluctuate as well.
Okay, yeah, thanks.
It's not random. There is, I mean, if it's physically, there is nothing random, let's say.
Okay.
Then there is a state, the circular state, which have a certain fold symmetry, and then in this case, you would see that they can rotate because there is no preferential symmetry. But as soon as you put a slightly anisotropy, they will stay in the same always, and you repeat, and you get always the same,
Okay.
Right.
Yeah. Thank you.
So. I think we're shortly going to move on. Francesca, I'm just going to take my premise. It's just a very quick question. So related to Paivi's question, and then we'll move on because we had a break. So from your connection, in your pictures when you show the hexagonal structure coming up, Paivi asked the question, of course, about the temperature. You know, a long time ago. We look at these things and we found that there's a phase transition if you increase the temperature from lower to higher, that this supersolid phase becomes a hexatic phase, a hexatic liquid phase. So there is hexagonal order in the system. So this is a lattice structure. When it melts in 2 stages. It creates a hexatic phase in which you lose translational order, but have rotational order, and then it melts into a normal liquid. Do you have enough resolution to see, the hexagonal structure here? Because these dots in the hexatic phase, they should be stretched in one direction versus the other. You understand what I'm saying? The question about the melting. Since the temperature, it seems to be if you're low enough to see the supersolid phase, you can, as you increase the temperature towards your normal state, you should have another phase, which is a hexatic liquid.
I don't know what is an hexatic liquid.
Hexatic liquid, I mean, 2-dimensional liquids, any liquids in 2 dimensions, it melts in 2 stages. There's the famous paper by Nelson about the melting of 2-dimensional lattices. So, I mean, I can send you my paper, but I mean, okay. The point is that if you're able to see the supersolid, as you increase the temperature, you should see the melting of the supersolid into a hexatic liquid before it goes to the normal state. And that melting
what we see is
manifests itself because you break translational symmetry, but you still preserve the hexagonal rotational symmetry.
So we have done this experiment in a linear chain. So what we did, what we call the life cycle of a supersolid.
No, so but it has to be 2D.
Yeah, exactly. So in 1D we did, in 2D we have not heated up the system. Yeah. We have not.
I think there'll be an interesting thing because there's a measurable way. I mean, if in your data here, it seems to be, quite nice. I'm pretty sure you can improve that a little bit more. And there's a definite prediction how this thing should look like if you have a hexatic phase. And of course, if you can image in real space, in the sense of
this is real space.
No. I meant to say if you can measure the distortion of these things in real space, if you look at each one of those bright yellow spots and you see a distortion into those things, you're going to see regions in real space where maybe these locations start to form, right? Okay. And then the system is going to start melting via the appearance of these dislocations as you heat up.
Yeah, okay. No, we have not done it. I mean, very interesting to see your paper. If you could send it to me, it would be interesting.
Yeah. Well, this is just building on Nelson's stuff. I mean, the original work for any two-dimensional lattice, you have a hexatic phase as the intermediate phase before you go to the normal state. And that was just an application of their RG ideas to this super solid problem. Anyway, good. So let's move on to the next speaker. Thank you very much, Francesca. I'm sorry that we lost you, but I think everything worked out okay at the end.
Thank you.
So our next speaker is Francesco Pederiva. He's going to be talking about imaginary time propagation of a quantum chip. So Francesco, we're going to have, again, the 20 minutes plus 5, and we start. And then we're going to compensate a little bit during our break time because we lost the connection. So thank you very much. Please go ahead and start.
Thank you to the organizers for inviting me. Can you hear me? Can you hear me? Okay, correctly? Okay. Yes. So
okay, we can hear you. We can see your slide.
No one is. Yes. Okay. This is a work that has been done mostly by Francesco Turro, who is a graduate student, PhD student here in Trento, and essentially is working in this collaboration that we have with people at Lawrence Livermore National Laboratory about essentially developments of quantum computing methods, mostly applied in perspective of applying them to nuclear physics problem, but of course. What you get is something that is applicable in general to any many body problem. And let's see how it goes. Okay. I will just very quickly say what imaginary time propagation is. You all know, but let me just spend a couple of minutes on that, and then I will tell you what kind of algorithm we have cooked up that can actually run on a quantum computer, and I will show you some results that have been run on a natural quantum chip, essentially on the IBM quantum experience, one of actually a number of the quantum experience IBM machines, and then I will show you also some results that instead are potentially relevant for nuclear physics, and this is sort of methodological talk. Don't get focused on the results, but rather try at least to understand somehow the kind of path that we are trying to follow to enable essentially the application of this kind of techniques in quantum computing. So imaginary time propagation is universally known. Essentially, you know that the basic idea is that you take time and apply what is called a Wick rotation, and you make time some sort of imaginary time. So instead of flowing along the real axis, imagine you have a complex plane, you flow along the imaginary axis. And essentially, if you try to solve the time-dependent Schrödinger equation in this new frame, what you get is something that is very similar in terms formally to to what you have when you try to solve the ordinary Schrödinger equation. But essentially, the propagator, instead of containing the time and some imaginary unit here, just contains this imaginary time. And the effect of applying this propagator to any state, essentially, is rather than if you want applying a time oscillating phase to each one of the components along the eigenstates of the Hamiltonian, is to kind of amplify or de-amplify, depends on the sign of the ends of the features of the spectrum, if you want, each of the states in the spectrum in such a way that essentially the ground state, the component along the ground state, after a while results the winner. And if you propagate for a sufficiently long time, what you have is a state that is made up essentially only by the ground state. This is a nice concept because it shows a way of computing ground states, of course, in a way that somehow seems to depend only on the Hamiltonian, because this is really, provided that the initial state is not orthogonal to the ground state, you can just go and project out the ground state. Of course, there are some features that might or might not be relevant, depending on how you do this, actually. This is a non-unitary operation. So, of course, if you start from a normalized state, you end up in something that is potentially diverging in normalization. So somehow you need to do something to correct the normalization by hand. For instance, if you want to stabilize some component that has an eigenvalue En, you could in principle divide your propagator by this quantity, and essentially this guarantees that the normalization of that component is stable. Of course, if n is equal to 0, this means that you end up projecting out the ground state while all the other components essentially decay exponentially with the imaginary time. And for large imaginary times, of course, you get, as I just said, a projection on the ground state provided the particular normalization. Now, as you all know, imaginary propagation is used and abused in many body physics. There are actually two main ways of implementing it. If you want, one is kind of, if you want, linear algebra based, and this has to do with the many variants of the power method, the Carnot method, Lanczos, whatever, which are very effective. Also might in principle provide a few excited states. It's nothing like a sign problem in this in general. They also have reasonably good scaling, but in general, if you increase the number of particles that you want to study, you need to get a larger and larger number of states, and this actually limits the direct application to a restricted number of bodies, which can be larger or smaller depending on how bad the Hamiltonian is itself. There is also a stochastic way of implementing this imaginary time propagation, which actually boils down to all the various flavors of projecting Monte Carlo. There are many which are very effective. They have a very good scaling. In general, if you have fermions, if you're lucky, you could say, okay, this should be scaling just like the number of particles cubed. This is really exact for many boson systems. However, I mean, when I say that you scale like n cube for fermion systems. I'm cheating because, of course, in stochastic methods, we have a strong so-called sign problem that actually makes the cost exponentially harder, exponentially larger when you increase the number of particles you want to gain. This is a general course of the business. And moreover, I mean, usually stochastic methods are not very easy to use for excited states, although there are ways in which you can obtain information about excitations. Anyway, you can find zillions of papers in which this is applied, starting from essentially lattice QCD, where in some way one is using the same concept to try to get essentially, if you want, masses of hadrons and similar, quantum chemistry, condensed matter physics, nuclear physics. So, of course, cold atoms, I didn't mention specific cold atoms, but there are many, especially quantum Monte Carlo calculations for those systems too. So, I mean, the imaginary time propagation is really one of the key algorithms for quantum many-body physics. And of course, it's sort of fashionable these days, but you immediately ask yourself, can we try to do something similar on a quantum machine? But why would you like to do that? Well, of course, as I just told you, that there are strong and severe limitations in general that are related to the fact that whatever you do, eventually you have to bounce your head into some exponential growth of the time that is necessary to complete the calculation. So, in general, if you find a way, if quantum computers could provide a way to overcome this problem, this would open the road to computing bigger systems. And if you can do that, essentially with a methodology which has sufficient overlap with what we know right now, how we know to apply imaginary time propagation right now, we can exploit all the experience we have to dig out information from the results. And of course, there are many targets. Imagine in mesoscopic physics. I was talking about neutron stars. Of course, it would be great to be able to use this kind of methods also to access information about nuclear and neutron matter, which these are systems is still extremely hard to compute in general. But you could also address, if you want to push quantum chemistry very far, you could start imagining a world in which you can really use quantum chemistry to address, for instance, life-related problems, by problems of biological interest and so on. Now, it's not that we are not, of course, the first to think of solving this problem. There are several implementations of imaginary time propagation or close alternatives, let's say, on quantum computers. This is not simple, and it's not simple for one of the reasons I mentioned at the very beginning. This is an operation that is non-unitary. And a quantum computer, which is, if you want, an experimental apparatus that provides essentially the evolution of some prepared state according to some propagator that you can control in some way. Well, of course, quantum computer in a very natural way, provides real-time propagation, not imaginary time propagation. And trying to implement a non-unitary operation on a quantum computer is definitely a hard task. It's sort of the opposite of what happens in classical computing, where it's very easy in some sense, relatively easy to implement an imaginary time propagation, but it's very hard to implement general scalable real-time propagation. And so these are some references to there are many different methods, hybrid methods, which are essentially variational methods based on the extension of the Hilbert space, which is what we also try to do. This recently, there's been this proposal of by the Ibm group of the story algorithm that is able to select essentially not just the ground state, but any state in a very efficient way. So there is a lot of work going on, and our two cents essentially are based, as I was saying, on this concept of extending the Hilbert space of the system that you are interested in. So essentially, suppose that you have some system that can be whatever you want, okay? A quantum dot, a nucleus, a drop of cold atoms, whatever. Or also some periodic system that simulates an infinite system. So essentially, the idea is, let's couple this the system to some thermal bath. Thermal bath doesn't need to be a huge collection of degrees of freedom. Actually, what we do is done. Assume that the thermal bath is just 1 qubit. Then this might not be the most efficient implementation, but and the idea is that if I take this combined system, so the system that I want to study and the thermal bath, and I apply some unitary transformation to a unitary transformation that actually can run easily on a quantum computer, but a unitary transformation that essentially has the effect of taking out from the system, if you want, the probability to find the system into some excited state and move it away to the thermal bath. This is done actually using a procedure that implies some measurement, okay, as we will see in a moment. But essentially the idea is that if you apply this unitary transformation on this isolated system, altogether the system is isolated, in such a way that you can really just move away probability from the excited state of the systems to the thermal bath, I will end up with a sort of cold system. So you can imagine that you have a hot system initially and refrigerate it. So this algorithm is a sort of quantum refrigerator. Okay. So you pump out somehow energy from the system you want, and you move it somewhere else. But you do that assuming that the overall system is isolated, so they can be described in terms, and its evolution can be described in terms of a unitary operator. So this is sort of the general idea. So this is like a quantum refrigerator in some way. So what happens? More formally, what you try to do is to take your state, which I mean your system, sorry, which is described as some state psi s, which if you want to work on a quantum computer, typically is a multi-qubit state representing a system you want to investigate. So just have some, imagine that you have states in a cavity or whatever system, quantum system that you can control. I call that a multi-qubit, okay? The thermostat is essentially an extra state, an extra qubit that is coupled to the initial system. So suppose that you take this extra system, this that we call ancilla, what I call the thermal button, and you put it in the ground state at the beginning, and you just build up the state that describes the initial condition for the quantum system. I mean, the ground state, this zero state of this qubit, is conventionally taken as if you represent it in a sort of spinorial formalism as the 1-0 state, the up spinor. Somehow conventional, as I said, I mean, there's nothing very deep in that. Then what you do is to apply a unitary transformation. So forgive me the logical leap here. Of course, it will become long, but on a quantum computer, this is exactly what you do. I mean, you can engineer some poles, for instance, that you send into your quantum system that sort of has the effect of making the system evolve according to a unitary transformation that is the one you want. So it's possible in a quantum computer in general to engineer this kind of unitary transformations, and we have found out that this kind of structure, which you see essentially contains the propagator, the imaginary time propagator that appears in the solution of the imaginary time Schrödinger equation, plus some normalization factors, let's say.
Francesco, just to remind you,
oh, yes,
to wrap up. Thank you.
So you can prove that this transformation is unitary, actually, and you can prove that what you have, if you take again the long time limit for this propagation, is a projection onto the ground state. Now, again, the projection onto the ground state means that you have to measure in the end the probability of the system to be in some state, and essentially before doing that you have to go through here a step which tells you that if I measure this auxiliary qubit in the ground state, then that is the system will be found in a state that essentially is closer to the ground state than the initial one. If I measure the auxiliary qubit in an excited state, I just forget it. So restricting the measurements of the system to states of the total system in which the auxiliary is the ground state provides a projection onto the ground state. This is sort of There is an interesting feature here that I just want to mention quickly. The propagator is exact. There is no need of providing a total decomposition. So you can just do this in one step. You decide the tau is to take a large tau. You just do this operation and go. So there are different ways in which you can implement this algorithm. You can expand. So in a standard computer like IBM, for instance, you expand in a set of gates, in a set of unitary operations that are already there for you. And so it's a sort of compilation. And so you can compile this unitary transformation into a set of gates, or you can do something more experimental in the sense that you can build your own gate if you want. So apply directly this transformation on the machine. So I just told you that what you do is the results are obtained by measuring the state of the system whenever the state of the auxiliary qubit is found in the ground state. So you can actually find the probability for the system to be in a certain state. And these are the results that is obtained on machines like the IBM. So just to explain you very quickly what this plot means, without commenting the numbers, if you start from an initial state, which essentially is so this is okay. Just let me tell you for what this is. I mean, this is the ground state of the hydrogen atom expanded on a two Gaussian set. Okay, so there are only two coefficients, so we can actually model the ground state of the hydrogen atom on a single qubit. So our global system is made up of a one qubit that describes the ground state of the hydrogen atom and one qubit that is this thermal bath. So essentially, you start from a state in which you have an equal probability of having both states up and down of the system, the qubit that describes the system, and then you make this evolve. And essentially, the result of the evolution gives you the correct coefficients that describe the orbital of the hydrogen or the ground state of the hydrogen atom. So this is a sort of interesting finding, because it's not obvious that this kind of transformation actually gives you the result you expect. I mean, then there are several things that one could check out. I mean, the fact that these quantum machines these days are noisy, so you cannot expect to have exact results because of the fact that the quantum machines are not perfect. So what you get are approximations. Here is just a plot that shows that the results depend actually on the machine that you're using. Let me just keep this, and let me just say that you can apply, and we applied, for instance, a similar concept to describe the evolution, actually the ground state of the spin state of two interacting neutrons, neutrons interacting with a realistic potential. And say, one can see the same, in this case, the spin, since we have two neutrons, the space that describes the system is made of two qubits, and you have to couple to a third qubit. So, but again, you obtain similar results that actually confirm that this propagation works. So let me skip this as well. Let me just conclude. So imagine time propagation of quantum chip can be implemented as a unitary transformation. You don't need to play too many games. What you need to do is to essentially couple your system to a thermal bath and try to find a transformation that in the end has the effect of, if you want, cooling down the system, which is actually the effect that the imaginary time propagation has on any quantum system. And okay, we have found the important thing that we found very nice and simple form for this transformation. We applied it to a couple of simple systems. The ground state of the hydrogen atom expanded in terms of two Gaussians, and two interacting neutrons with fixed distance, which this especially the second is already sufficiently serious Hamiltonian for this kind of experiments. The algorithm is robust, reasonably accurate, even with noisy machines, the machines that are available for experiments these days. And of course, what we have not done so far is a serious study of the scaling, because this is really the big question. I mean, you invent an algorithm, and then the next, I talked to you about neutron stars at the beginning. I mean, from the hydrogen atom to there is a long way ahead. And this is, of course, what we need to try to do in the future, but this depends also on the availability, of course, of machines and computational resources, which maybe not right around the corner for a serious study of this kind. Okay, thank you for your attention.
Okay, thank you, Francesco, very much. We have time for one or two quick questions. Okay, Zora, please.
Hi, Francesco. Thanks very much for the nice talk. It's an interesting work. So regarding this scaling statement that you just made, just trying to understand this, if you wanted to use this in Schiller as sort of your thermal reservoir, does that mean that if you have a larger system, you need more enchillas? It seemed like with just a single qubit, you could actually perform the calculation for a 2-qubit system, for a 2-qubit size. Do you have any idea how to scale sort of the size of your thermal?
I mean, you don't need, I mean, as it stands, a larger system doesn't necessarily imply that you need more than 1 qubit as a thermal path. However, you might need more than 1 qubit. If you want, for instance, to operate a totalization, or you have to operate a total decomposition of your propagator for whatever reason. That, for instance, is sort of simpler to implement if you use a number of ancillary qubits. But that's not the problem of the scaling. I mean, the problem of the scaling, of course, is more related to for instance, how this gets with noise and similar, let's say, because.
So let me understand this. So
and,
this
and of course, the time that it takes to implement it. Yes.
So I guess so that this Enschiller qubit, was that actually sort of providing the thermal bath to the system? So you're saying even if your system is like 1 million qubits in size, you still need 1 single qubit to provide that bath to thermalize your evolution?
Yes, the problem is that if you have 1 million qubits, then you have to couple the whole thing to that qubit, and that is going to cost you order millions of CNOTs. Okay, so that is of course going. I mean, the problem is that you don't. This is naturally adding complexity because you have to entangle the whole system with ancilla.
So it's not like the size of your bath. So I guess it's not like the size, the Hilbert space that defines the size of your bath should be comparable or larger than the size of Hilbert space that you're simulating or thermalizing. It just is enough to just couple a small Hilbert space to whatever large Hilbert space you're thermalizing. Is that?
Yes. Because I mean, the key is the non-selective measurement process. That's the point. I mean, it's the fact that you have this extra qubit that you use essentially to throw away the states that essentially would bring you against lowering the energy.
Okay.
Okay, guys. So I would ask then people to hold on them to other questions to Francesco in the discussion session.